Okay, good morning, everybody, or good afternoon, or good evening, no matter what time zone you're in. I'd like to welcome you all to the third webinar in the HIWeather webinar series. Our webinar today is about user-oriented evaluation of high-impact weather. And if you've been following the webinar series, you might have joined the ones about communication and impacts and vulnerability. And in the next 2 weeks following this one, there are 2 more webinars about hazard forecasting and processes and predictability associated with hazardous weather. So I'd also like to note that today's webinar is joint with the 8th International Verification Methods Workshop, which is a 2-week rolling workshop around the clock on forecast verification. And so I'd like to thank Barbara Casati and the workshop organizers of the verification workshop for allowing us to be joint. I'd also like to thank my co-host today, Martin Wegman from WMO. Without Martin's help and assistance, I think this webinar series would have been pretty impossible. So my name is Beth Ebert. I'm a senior scientist at the Bureau of Meteorology in Australia, where I'm currently leading an effort in the Bureau to uplift our verification processes and, importantly, our communication of verification results, both internally and externally to the people who use our forecasts. Before joining the High Impact Weather Project, I was a member of the Joint Verification Working Group, and I'm still connected to that through the WWRP. I'd now like to invite the other presenters to introduce themselves, so I'll just call them by name. So Barb, would you like to introduce yourself?
Hi everybody, I'm Barbara Brown. I'm a senior research associate at the National Center for Atmospheric Research, where I've worked for a large part of my career. And I'll be talking about some work we did on tropical cyclones, one of the major projects we had in our group, and looking at user-relevant forecast verification.
Thanks, Barb. Juli, would you like to introduce yourself, please?
Hello, everyone. My name is Julia Chasco. I'm the head of the Meteorology and Society Department of the National Meteorological Service of Argentina. I'm a member of the High Impact Weather Evaluation Task Team. I'm co-chairing the Socioeconomic Research Application Working Group of the WWRP program in WMO. My background is associated with social sciences. I'm a sociologist and MPP, and I work with disaster risk reduction initiatives in the context of weather and climate service provision.
Thanks, Juli. And Amanda, would you like to introduce yourself, please?
Hi, I'm Amanda Sims Anderson. I work at the National Center for Atmospheric Research in Colorado in the US. Worked with Barb for a number of years. I specialize in looking at verification of decision support systems and in road weather, and I'll be talking about the work we did to verify our coupled fire atmosphere model for the state of Colorado.
Thanks, Amanda. So the way that our webinar will work today, each of us give about a 15-minute talk. Each talk will be followed by questions from the audience. Please use the chat to put your questions in. If for some reason the chat doesn't work, you can email it, and hopefully one of us will be able to receive that and find your question. Apparently the Microsoft Teams hands function doesn't work for live events, so please do use the chat. And not just to pose questions, but if you would like to chat with each other or make observations, comments, the chat is a really great way to do that. And we'll be following the chat, in order to identify questions for the speakers. We have as much as 2 hours. And so if we do have some time after the 4 talks, which I expect we will, then we can go into some general discussion after that. So I will start off with an overview of the activities of the evaluation task team in HIWeather. Our activities are largely focused around the value chain of information, connecting observations all the way out to decisions in response to high impact weather. And so the sorts of questions that we are looking at, we are starting to, we develop appropriate verification methods for new kinds of forecasts. We also are quite keen to build users' trust by providing more user-focused information about the quality of the forecasts. A new thrust is using social media and non-standard data, particularly for high-impact weather, where you might be thinking about storms or floods. The typical meteorological measurements of temperature and humidity aren't really what you need. So there's a whole lot of new exciting data from social media and impacts and so on that we can use to evaluate these types of forecasts. We also have a big emphasis on social science to try and understand the decisions that users make in response to high impact weather. You can have the best model in the world, but if you don't do a good job with the warning and the communication and the understanding and the trust, then you may not get the response that you're wishing for. And then finally, we have a cross-cutting perspective as well, trying to apply methods and develop methods to look right across the whole warning chain, and linking the different communities that are working on different parts of the warnings, whether it's the meteorologists or the hazard community or the media or health. There's lots of communities that are involved in getting a warning made and acted on. So I'll go fairly quickly through the types of activities that we have been working on over the last couple of years and encourage you to maybe contact some of the people who are identified on the slides if you're interested in knowing some more. So starting with my first question about verifying new kinds of forecasts, there's been a lot of activity in the last 5 years or so applying spatial verification methods, which have been a very active area of research over the last decade or two. Now moving those to high-resolution ensemble forecasts, because that's the way, that's the frontier of weather modeling. And so the Mesovict project, which was joint with the verification working group, was looking at traditional variables like precipitation in wind, but now from high-resolution ensembles and in tricky terrain, the mountains of Europe. And this project is now finished. It was able to show that spatial verification methods that were developed for deterministic forecasts were largely able to be adapted to verify ensemble forecasts, which is excellent news. We also tested on the uncertainty of the observations by having a few different spatial analyses as the truth data set, and showed that the way you handle the truth or which choice of truth you use can have a large bearing on what your conclusions are. So that's something that we need to be quite careful about. We also have a member who's, Chiara, who's very involved in the UMetNet SRNWP EPS2, which is having a focus on now these high impact weather phenomena of thunderstorms and fog, where again, it's no longer state variables that are of highest interest. It's things like storm occurrence, extent, timing, intensity, things like that. And again, other kinds of measurements, such as lightning or visibility or impacts or crowdsourcing, are the kinds of data that you would use to assess how well those forecasts were performing. We've had some collaborative activity between Australia and the US on fire spread evaluation. And this is a new frontier of coupled modeling between the NWP and fire behavior models. And in fact, in Colorado, you'll hear from Amanda later the details of this work. But we've been able to use some of the simpler metrics that we use in meteorology, such as threat score or some of the spatial methods, to have a look at the fire areas that are predicted by the models and their sensitivity to the weather conditions, but also things like the fuel conditions, the ignition, location, and timing, and so on. Moving on to user-focused verification, we ran a challenge a couple of years ago for the best new user-oriented forecast verification metric. And we were very happy that we had 17 entries from 11 countries. The winner was an entry that was to do with measuring sea ice extent and the position of the sea ice edge. But it's a technique that can be adapted to anything which has an edge that you might want to verify. So that was pretty interesting. Other entries were rain-free window, thunderstorms at airports, and a weighted percent correct for seasonal forecasts. Barb will be talking in her talk today about user-driven verification of tropical cyclone predictions. And this was work that they did, the NCAR did with the National Hurricane Center to help them select which models they wanted to use in operations. And so the users in this case were operational forecasters. And they asked a number of questions, and Barb will say a bit more about it. But it wasn't just the standard, what was the error? It was comparing one model with another, and what did you want to know? Well, which model should I use? And that's a different question than we normally answer. So we'll hear more from Barb about that. I'd like to call your attention to the second verification challenge. So this is the successor to the first one, and the theme this time around is using non-traditional observations in verification. So we're looking for new metrics. It might not be a new score, but it might. But we're particularly encouraging people to have a look at the social media or third-party networks, things like that, that can be used to say something about not just high-impact weather, but any kind of weather. The deadline for entries is 30th of April next year, so there's plenty of time to join if you're interested. The prize will be paid attendance and a keynote talk at the next International Verification Methods Workshop, which should be in about a year from now. And it's open to teams or individuals, and if you want to know more, there's a website here, or you can just Google International Verification Challenge and it should come up. Again, on the theme of non-standard data, one of the really exciting activities that Helen Titley and Joe Robbins have been doing at the Met Office for a number of years, but we're using it in HIWeather, is the Global Hazard Map, which is ensemble forecasts from a few global ensembles combined to look at extremes of weather and then the impacts that might be associated with those. So there are tropical cyclone forecasts in there, extreme heat and cold, extreme precipitation. And the evaluation that they've written up used a combination of approaches: traditional verification for rainfall, which is something that many of us are do every day, but they also pioneered some work in impact-based evaluation. And they collected a database of community impacts, which I understand was a lot of work, and then used that to verify polygons that were identified from the ensembles. And they've got very encouraging results. So I would encourage you to have a look at that work. I think it's pretty exciting. Another European project, again, so I should say that not all HIWeather projects originate with HIWeather. We're leveraging a huge amount of really great work that's happening out in the community. And so when people who are involved in those projects are part of the HIWeather project, then they bring that knowledge and that opportunity for others to participate in it. So the European Weather Observer is collecting crowdsourced observations of weather. This is part of the UMetNet activities, and Rainer Kaltenberger is our member in that. And that the idea is to try and standardize and collect that information to support the warning services right across Europe, and using standard displays and colors and things like that. On the topic of understanding user decisions, we have a very active couple of people in Switzerland who have been doing some fantastic work in this. And I particularly mentioned Philippe Weirich, who did his PhD as part of our HIWeather evaluation task team with his supervisor, Anna Skolobig. And they did a number of social science experiments to understand the way people respond to warnings, and they might have been sort of survey type experiments or serious game experiments, and they did also some real-time trials of how people actually respond to warnings. And so a lot of this work is written up. My last slide, which I won't talk to, has got a long list of references that you can follow if you'd like to learn more about this work. But one of the exciting things, I think, was some work that was suggesting that you can use these laboratory experiments in a valid way to understand the way people would respond in real time to warnings. Another very exciting development, which you'll hear about from Juli in her talk, is the development of the new early warning system in Argentina. I won't say a lot about it because Juli will give a whole talk about it, but during the life of HIWeather so far, it's gone from being a very traditional jargon text type warnings, which were maybe not that effective, to now graphical and very user-oriented because it was co-developed with the emergency managers and members of the public and so on. So I understand it's launching next week or the week after next. Pretty exciting times. A few things, as I mentioned at the start, the warning value chain is kind of an underlying theme for the evaluation task team. And so it's very interesting for us to look across different parts of the value chain to see where value is being added. And so a project that Helen Titley is looking at for her PhD is how tropical cyclone heavy rainfall can then lead to flooding, and using the ensemble rainfall forecasts to drive ensemble flood forecasts, and then understanding how those ensemble flood forecasts can be used to create warnings that are more effective. There's also been in Europe a recent survey on impact-oriented warnings. So trying to not just say what the weather will be, but what the weather will do. This is a phrase we're hearing a lot as weather services move towards more impact-based forecasts and warnings. And the survey that was just written up and published this year indicated that most of the European countries are moving in that direction, and there's a lot of coordination going on to try and make sure that this is done in a way that is best practice right across the region. Socioeconomic benefits is one of these holy grail type topics. I think we all want to know what is the monetary value, the value in terms of lives saved or property protected from doing warnings. And this is something that we'll be working on a little bit more with some value chain work that I'll talk about in a minute. But I'd like to remind people about the SARA workshop, which is coming up next year. If you were listening to the communication task team, you would have heard Martin Gerber talk about this. But it's very much like the series of verification workshops, where it includes a tutorial session of a couple of days, followed by a scientific conference of a couple of days. And the intended audience would be practitioners, meteorologists. And so you can see the topics there. It's an interesting mix of mostly social science, a little bit of more physical science with things like impact modeling, but again, not just traditional weather science. It's really taking that weather science and making it real for the user community. And this is, I think, likely to be online, but I'm not absolutely sure about that. So I want to finish off talking about a brand new project of the HIWeather. It's one of the flagship projects of HIWeather, and it will be being led by our task team on evaluation. And using value chain approaches to evaluate the whole end-to-end warning chain, and it's joint with the SARA working group. And the aim of this project is to describe, measure, and ultimately improve the effectiveness of warnings by looking right across the whole chain for where improvements could be made, and focusing particularly on the links in between different communities. So I sort of glossed over in my earlier slides, but I wanted to mention the Green Mountains, which many of you will have seen if you've heard Brian Golding talk about the value chain. And he's one of the HIWeather co-chairs, of course, where the mountains indicate different capabilities or communities that are working in an area that's relevant to warning. And the bridges represent the flow of information, or maybe it's data, between the communities. And the bridges can be variously higher or lower depending on the effectiveness of that information flow backwards and forwards across that chain. So it's not just going down the chain, because the people who are receiving it also need to be communicating back up the chain about what they need, how they use it, and hopefully co-designing that information flow. And so this project is going to be collecting information on actual high-impact weather events where warnings were made, maybe some even where warnings were made that the event didn't occur. And we're trying to collect as much data as we can from all of these different parts of the warning chain, so that we can evaluate it and try and understand what's working well, what's not working well, and develop some guidelines for best practice use of this value chain perspective. And we're really happy and delighted that Sarah has got a strong interest in this, and in fact they'll be doing a lot of the core work on value chains themselves. So how do you use a value chain to as a framework for organizing your data or understanding how information flows? And we're very hopeful that as part of this, we'll have some good methods on measuring the effectiveness of the value chain and guidelines for users onto how to do that and how to create their own case studies as well. In the long term, we'd very much like to link this with a WMO activity that's just getting going as well, called the Catalog of Hazardous Events, which will become an operational international system linking weather events with impact information from insurance and so on. So that is a big international activity from WMO focusing on part of the value chain, and we're going to be trying to enrich that, at least for some of the events, by looking more broadly and widely across the value chain. So this is my last slide for today. I'd like to encourage everyone online to consider joining some of these high weather activities, whether it's the challenge or participating in evaluating the global hazard map, the European Weather Observer, the SARA workshop next year, the value chain project. We'd be very happy to have as many people involved in that as who would like to be. And I'd also call your attention to the 3 high weather workshops coming up in the start of December. And if you're interested in joining those workshops and making a presentation, abstracts are being accepted for another week or so. You can send them to Martin Wigman or look at HIWeather.net for more information about the HIWeather workshops. I'll just flick to the last slide. I won't stay there, but the slides will be shared. If you want to follow up on any of those publications, then you can download the slides. So with that, I will stop sharing and see if there are any questions.
I don't see any questions at the moment, Beth.
Okay, thanks, Mark. We'll give it a couple of seconds since we know there's this delay.
Yes, maybe I could ask one while we're waiting.
All right.
If you're interested. No, I really like that sort of view of the value chain. It's really nice sort of to get the idea. How probabilistic is it? Does it all the way through? Are things probabilistic, or can people cope with that, or is it still deterministic?
I would say it depends. It depends on who your users are. Ultimately, decision is deterministic.
Yes,
usually.
that's the last one.
Yeah. And certainly the trend is to become more probabilistic. I think until we start looking right across internationally, we won't have a sense for how widespread that is. But I think for well-developed, sort of world-leading net services, probabilistic is where they're at right now, or desperately trying to get to. So we will be encouraging that, and a lot of our evaluation will be probabilistic as well. I should point out that evaluating impacts is kind of by nature probabilistic. There's so much uncertainty with the impacts that you kind of have to treat them in a probabilistic way.
Okay, thank you. We have a couple of questions come through now. I guess I should read these out, should I?
Yeah.
So one from Michael Foley. Responding to warnings. During COVID, we have seen validation of the impact of community restrictions based on analysis of Google or Apple phone location data. How much people are traveling? Has anyone looked at correlation between warnings and change of travel behavior as measured in this way?
Thanks, Michael, for that question. That's a good one. It's certainly being talked about, and I think there probably is some research on that. I'm not sure if it's being used in operations anywhere yet, but I believe there is some research on that, and that's certainly travel patterns. Definitely one of these things that we'd like to look at. I suppose getting hold of that data is not always easy, but it's something that I think universities are starting to work on for sure.
Okay, we have another one from Rini Sieber, is it, from McGill? Curious if anyone is working on ontologies of these high weather events. In our project, we compared old and new snowstorms and found that we first had to define a storm that covered the full temporal extent of the storm. Not necessarily easy to tell when the storm starts, but sub-daily observational data. I'd argue that the need for ontologies is even more important when using social media data in unsupervised classification, because you shouldn't rely on the unstructured content to determine what constitutes an event. I'm sorry, I was struggling to keep up with that question myself. I
think I get the gist of it.
Gist,
and
yes. Okay.
I don't know to what extent those things do exist already, or how much standardization will be possible. Certainly for our value chain project, we're going to be trying to organize data in ways that will enable ontologies to be done with them by collecting information about start-stop location, what the forecasts and warnings were, and so on. But I would agree that that's something that we'll need to do in order to make sense of things. And I don't know whether there are within WMO, within the DRR part of WMO, groups that are working on specifically that. I know that there's a new publication out this year that is classifying hazardous events and defining them, and that might be a first step in getting an ontology that everyone can use and agree on.
Okay, we have one more from Robert Rogers. The value chain seems to be the idea linking together all of these webinars. There are different locations along the chain. Would you agree?
Yes, absolutely. And we've used that in our HIWeather workshop in Beijing a couple of years ago as well. The evaluation test team is interesting because we probably are a little bit unique in going the whole length of it. But yes, that's been a very useful construct. I should mention too that while we've been presenting it as this linear flow, that in fact it's actually a network. It's much more complicated than that. And so the value chain project will probably continue to use a linear framework, but recognizing that a lot of links are going, right across to other areas and many different players and so on. I would refer you to a paper by Rebecca Morse in BAMS a couple of years ago that really describes how complicated it is. Yeah. And
a question from Brian Golding, if we've got time. So this is, I think it was responding to Michael before. He says there was an interesting study using this sort of data of how people responded to Superstorm Sandy in New York, distinguishing those who evacuated from those who stayed and what each group were putting in their social media posts.
Yeah, that's a really good example. And that's probably a great case to include in our database for learning have what works and what's not working so well.
Yeah, very interesting. That's it from the Q&A here.
Oh, thank you very much, Mark, for that. I think we'll go on then to our next speaker, who is Barb Brown. So, Barb, over to you.
Thanks, Beth. I'll try to share my screen here. There we go. Hoping you're seeing it now.
Yep.
All right. So one problem I have is that Beth is blocking part of my screen. But I'll manage, don't worry. So I'm going to be talking about some work we've done at NCAR on user-driven evaluation of tropical cyclone predictions. And this is work I did, it's with a large group of people, so not all represented here by any means. Louisa Nance is the co-author on the work, and Christopher Williams, who, well, Louisa is the director of the Developmental Testbed Center, a national organization to test modeling and forecasting. Christopher Williams is now studying at the University of Florida Department of Geography, but he did some great work on this project. So the picture I had on the first slide was something that would be recognizable to anybody who's done work in hurricane, especially this year. This is Hurricane Laura that I think it made landfall on the 27th of August. So this picture is just before it made landfall, and it was the 10th strongest U.S. hurricane landfall on record, which led to a bunch of deaths and a huge amount of damage. And so a lot of that potentially was related to the intensity of this storm, a lot of that damage. So predictions of tropical cyclone track and intensity are very important for planning evacuations, protecting life and property, and so on, as all of you know. The goal of this presentation, though, is to consider user-relevant, meaningful ways of evaluating NWP guidance to aid forecasters in making the kinds of predictions that they made for this forecast for this storm as well as other storms. So I'm going to present a simplified version of the value chain that Beth showed just a few minutes ago, which is one that was developed by Jeff Lazo a number of years ago. And the reason I'm showing it is I think I want to make a point that there are a few things that there's some spaces. I think there's more complexity in each of these boxes, undoubtedly, than what is shown here. And the complexity I want to talk about a little bit is in the modeling and forecast part. In particular, what we're talking about in this particular project is the NWP and OBS that go to forecasters, and then forecasters make decisions about their forecasts and their warnings. And that's exactly what happens at NHC. That the forecasters get lots of information from the initial steps, but then they do their work and create the warnings and the forecasts. So this study considers the question of how verification information can best inform and facilitate the use of NWP guidance by forecasters. So that's our goal, is to look at this little bit of the value chain. this extended value chain. So the idea of user-relevant verification has been around for a long time. We published a paper back in 2008 that Rebecca Morse was the lead author on, where it appeared, and then it's also in a paper that we put together that Beth was the main author on, that was published in MetZ in 2018. So I'm not going to go through all the details of this because we could spend a lot of time on each of these levels and argue about whether they make sense or not. But what I'm going to be presenting today is what I would call a sort of level 3 activity, where we're looking at user relevant verification approaches and measures. And another way to think about these is that they are actually user driven, particularly in this specific example that I'm going to be describing. So we're not quite with this getting to the level of actually estimating the value of forecasts by looking at the economic impacts of decisions or economic or human impacts of the decisions. But we are defining verification approaches based on what the needs are, the specific needs are of a set of users. So as I just said, the idea of user-driven or user-relevant verification approaches is that they consider information needs of specific users rather than applying a standard, a one-size-fits-all approach to all forecasts. So for example, the common use of the mean squared error or anomaly correlation for NWP might not be adequate to give the right information, for example, to hurricane forecasters or tropical cyclone forecasters. And these approaches, in order to develop them or identify them, require an understanding of what the user's questions are about the quality of the forecast, so that we can define measures that answer those specific questions. So just a little bit about the project that was the driver for the work that I'm going to describe here. Is the Hurricane Forecast Improvement Project, which is an ongoing project. It was initiated in 2007 to try to significantly improve forecasts of tropical cyclone position and intensity predictions. Those were the initial goals. And initially, we wanted to be able to demonstrate significant improvements in predicted track and intensity. And I bolded intensity there because I'm only going to present some description of methods that we developed for intensity, evaluation of intensity predictions. You can see on the right-hand side there a diagram that shows intensity forecasts for a particular tropical cyclone. I don't even remember what storm this was, but you can see a variety of model-based forecasts of how intense the storm was going to get over the forecast period. You can also see the best track in the black, which is what the Hurricane Center forecasters predicted. And you can also see in the black dashed lines what the actual best track was. So the best estimate of what actually happened. So you can see these forecasts were pretty far off in terms of how this system actually evolved. So the goal of the NCAR project was to provide guidance to the National Hurricane Center, or NHC, to help them select experimental models that operational forecasters could look at during each tropical cyclone season during this project. And so basically, the HFIP project funded a lot of different modeling groups to try to improve the NWP that was available for the forecasters to look at. So each year, NHC wanted to check out these models to make sure to choose the ones that seemed to be most promising and that also wouldn't degrade the information that was available to the forecasters. So one of the goals was to select models that would do no harm. So we didn't want to give the forecasters information or put information in front of them that was pretty clearly not going to be useful or could be even negatively useful. So the approach to this project it evolved over time. So each year, I think we did the project for 7 years, did these evaluations. And the approach was to work with NHC staff to identify questions that were relevant for their use operationally, for use of these models, and then to develop verification approaches that would answer those questions. And the goal was to compare the experimental model performance to the performance of some baseline models, which were modeling systems that NHC was already using and had confidence in, or some confidence in anyway, enough confidence so that they were using them and referring to them. And each year, the forecasters, the modeling groups, produced 3 years of retrospective forecasts. And we also had baseline forecasts for those also the same 3 years. The models were evaluated each spring before the start of the hurricane season. And then the models that were chosen that satisfied the criteria ended up being demonstrated to the forecasters during that next hurricane season. So some of the questions that we asked is, as this project evolved and we worked with the managers and the forecasters, were things like, does the experimental forecasting system perform as well or better on average than the baseline models? Does the experimental system have more or less outlier events? And how does the candidate model rank with the baseline models? So is it much better, much worse? Does it consistently have some rank within the other models? And those are some examples. We did the project was actually a little broader than that, but these are the things that I'm going to talk about now. So the next few slides will show some examples of results for a single candidate model, what we call an experimental model, and its predictions of TC intensity in comparison to 2 baseline models. So the first question that we were interested in asking, as I mentioned, was whether the candidate model, which we call E1, have smaller errors than the baseline models, or at least no worse errors than the baseline models. And here we're calling the 2 baseline models that we're looking at B1 and B2, so baseline 1 and baseline 2. And what I'm showing here is the traditional intensity verification that I think is still done at NHC and by others, looking at average intensity errors as a function of lead time. So we see in black the B1 on the left-hand side, B1 versus E1. E1 is in orange. And on the right, B2 versus E1, where again, E1 is in orange. And you can see that it looks like in both cases, the experimental model performed better than the baseline model, although the error difference was not much smaller in the comparison between E1 and B2. So it looks like, you know, pretty good. If this were all we were going to look at, we would say, yes, go for it. This experimental model is great. But if we actually consider the uncertainty in those verification results and put confidence intervals on them, we get a much different story. So let's just look for now at the orange and black lines at the top. And you can see that there are confidence intervals on each point, and you can see that there's overlap between the black and the orange lines, which suggests that none of the differences are statistically significant. So that's true for both comparison B1 and B2. So that contradicts the results that we saw in the previous slide. But if we do pairwise comparisons, as shown in the blue lines, where we've put confidence intervals on the pairwise differences between the forecast errors at each time, we find significant differences for most lead times relative to baseline 1, but only significant differences for some lead times for baseline 2. So it's quite a different story than you get by these intermediate approaches. So another question that was of great interest to the forecasters and to the managers was avoidance of whether there were going to be more busts with the baseline, with the experimental model than with the baseline model. So we define busts as having significantly large errors with the forecast. And you can see if we look at baseline 1, we definitely are seeing more errors with the baseline model than with the experimental model. So in this comparison, the experimental model seems to be greatly improving the performance. And whereas on the other hand, if we look at baseline 2 versus the experimental model, we don't see the same kinds of large errors or differences in large errors than we did with baseline 1. So it definitely seems to improve greatly in this regard over baseline 1, but not so much over baseline 2. So the forecasters were also interested in what is the frequency of, let's see if I can go back here. How frequently were the errors large for the experimental model relative to the baseline models? And so what this diagram is showing is the frequency of cases where baseline model was better than the experimental model, or the experimental model was better than the baseline. And so these have confidence intervals. These are 95% confidence intervals for the question of errors smaller by at least five knots. And so you can see for most lead times, particularly after 48 hours, that the frequency of large errors was much smaller for the experimental model than for the baseline model. I forgot to mention that the gray line shows where there was a tie, and so there's significant improvement by the experimental model over the baseline model here, which gives confidence that overall, in general, the experimental model is going to do okay. If we look at baseline 2, we get a little bit different story because there are lots and lots of ties, which suggests that the baseline model and the experimental model essentially performed very similarly to each other. But in those cases where they weren't tied, in general, the experimental model did better than the baseline model. So these kinds of results give confidence that E1 is probably not a bad forecasting system to look at. And finally, we looked at how the experimental model ranked in comparison to 3 baseline models. So I've added a third one in here. So there are four models that we're comparing, E1 plus baseline 1, 2, and 3. And so this diagram is showing the percent of cases where the experimental model ranked best or second best or third best or worst. And so we don't have a criteria for how much better, but if the errors are smaller by some amount, then it's counted as better. And what we see here is that for some lead times, it was second best. The experimental model was second best significantly. Again, we've got confidence intervals around these ratios. And then, so for those shorter lead times, it was often second best. And for the longest lead times, it seemed to be performing better than all 3 of the other baseline models. And I think a useful piece of information is how often was the model the worst among the 4. And here it suggests that it's something less than 20% of the cases the experimental model was the worst. So some conclusions from this is that it's really important to look at the uncertainty in these verification measures, especially if we're trying to influence decisions. That makes these decisions more defensible. Evaluating user-driven questions gives us strategies to make rational choices about which forecasting system should be used for particular applications. I think this is not unique to this particular study, but is a broad kind of idea that I think is worth following up on for other kinds of projects. And then simple or standard questions that we frequently ask, such as about average behavior, may not meet what the user needs are. So developing user-driven approaches that involve really working closely with decision makers really are important. And I think for high impact weather, that's really important. And for the whole idea of the value chain, thinking about user-driven approaches to get this kind of information. It takes a lot of work, but I think it's worthwhile. The approach here was, I think, could be a model for other kinds of applications like this as a component of the value chain. So that's all I have, except to give some thanks to many people who contributed to this, in particular the forecasters and managers at the Hurricane Center who took great interest in helping us with this and identifying the information that was important. So, and also the HIWeather project office and the modeling groups who continuously put a lot of effort into providing their forecasts to us. So that's all I have. Thank you very much, and I'll take any questions.
Hi, Barbara. We have a question from Brian Golding.
Okay.
He says, am I right in thinking that your metric for intensity is maximum wind speed? In light of recent published research suggesting that total damage is poorly correlated with maximum wind speed, are you planning on looking at other metrics of intensity, such as central pressure, which may be better correlated with damage?
We're not actually doing this project anymore. But I agree with you, Brian, that would be a good idea. And I think there probably are other kinds of other factors that should be considered too, besides just the intensity. As we've seen a lot of damage in recent years from precipitation. But that was there had been such a lack of improvement in intensity forecasts that that's why HIWeather decided to focus on that.
I have a sort of related question. Do you ever run a damage model itself, you know, with the truth sort of analysis and then sort of verify the actual damage like that? Can you do something like that?
I don't see why not. Yeah, but we have not done that. This really just stopped with the forecasters.
Okay. So we have another question from Tom Robinson. The errors for the E1 and B2 were flat from about 48 hours on. Is this typical of intensity forecasts? And if so, why is that? Why don't we see an increase in error with lead time?
And I don't have a good answer for that. I think if there's somebody on the chat who has some more experience with hurricane forecasts, they might have hurricane forecasting. They might have that some ideas on that. I'm sorry.
Mm-hmm. I don't know how we're doing for time. There's a couple more questions here. In fact, 3. Marianne Giraud, does that mean that you see that you should use operationally different models on different lead times?
It's possible if there was a strong enough signal that you should. I think our goal was really to show that overall the forecast didn't show an overall degradation. So I think that would be another kind of question that could be asked in the value chain work is, you know, is that something that should happen? And I don't have an answer right now, but you could if you had that ability and if there was enough consistency between the models so you weren't jumping around a lot. That's something we haven't evaluated is consistency in the forecasts, which is also another factor that people and forecasters are concerned about. It's possible that changing models for different lead times would make sense. I mean, we already do that moving from mesoscale models to to global models and so on for different lead times.
And then sort of following on from that, Michael Foley has a question. He sort of says that tropical cyclone forecasting typically uses the model consensus approach. So did you do any evaluation of the extent to which the new model improved on the quality of the consensus forecast?
Yes, there was some work done with the consensus forecasts, and I don't have results on that, but yeah, I think that would be one way that you get away from that issue of, the switching back and forth between models. Often you can get away from the jaggedness of that kind of switching if you look at a consensus, or even the jaggedness within a particular model if it's not being consistent from time to time. So it's again, what is the important factor that you're looking for? Is it consistency from time to time, or is it getting overall the best forecasts across all times? So it's tricky business, I think, and that's another thing that I think would be a good thing to evaluate as part of some of the work on the value chain.
So I just want to stop me if we're running out of time, but there's a couple more questions.
Maybe one more question, if that's all right, Mark.
Okay. So the next one is from Darren Griffiths. Operational forecasters can't look at an unlimited number of models. In the examples you showed, it looks like they should add E1 and possibly stop using B1. Having E1 and B2 or of similar standard seems more useful than just one of them. Any comments?
I think that the ultimate goal of the project was to select characteristics of models that would go into a system that would overall provide the best forecast, and then you would probably not have to be looking at as many models. So I know the forecasters are always going to want to look at more than one model, but it was mainly to try to improve the operational systems in general.
Okay, Brian Golding just gives a possible answer for why the errors don't increase with lead time, thinking that things may be saturated, errors may be saturated. But I guess you could reply to him later. Okay, yes. So that's it.
Okay, thank you, Mark.
Okay, thank you very much, Barb. That was great. So now I'd like to invite HIWeather to give the next talk about Argentina's early warning system.
Sure. Let me share my screen. So there it is. So can you confirm you're seeing the screen, right? Correctly?
Yes. Yes.
Okay. So today I would like to share with you the experience of working with decision makers in the process of creating an early warning system. I will try to summarize. Hold on a second, please. Okay, I will try to summarize the work that the National Weather Service has done in the recent years in working with users to improve our early warning system. I have decided to organize the presentation in a sequential way, so I will tell you how we have done this from the beginning. That is how we work to identify the weaknesses of the system. Then, once the Meteorological Service decided to update the warning system, what we have done in the last 4 years to manage to correct the vulnerabilities found. I will also share with you how we work with users in the months prior to the implementation, basically all 2020. And finally, how we will continue to incorporate the perspective of the users once the new system is implemented, which will be in a few weeks. So for a matter of time, I will only tell you some examples of the implementing techniques along the process that I think can be useful in any context. So I must apologize because it is possible that many of you have already seen this drawing in previous presentation of mine. I will explain why, because surely there are new people in the room and it is an exercise that I like very much for its simplicity and the amount of information it gave us. Okay, so in the left side of the presentation, you will see a text that is in Spanish. It's an all-weather warning from the year 2015. We wanted to confirm some system vulnerabilities. So in a workshop that we made with more than 100 emergency managers, we did the following exercise. We gave all the same warning text, that is this one, and we asked participants to individually draw the warning they had in a text on a map of Argentina. So the result, each participant drew a completely, as you can see, a completely different interpretation of the same warning. Some even divided the regions according to the severity of the phenomenon, others according to the time of arrival of the storms, and others just divided the different phenomena and just distribute them all over the place. So although this might seem funny at some point, it is a very difficult fact to ignore that everyone was misinterpreting what the forecaster had meant, or rather these warning messages sometimes are full of flaws. And these are some of the ones we identified. For example, we have extremely confusing coverage area. Users are confused about whether or not they are included in a warning. The warning are in text format, so there is no possibility of inserting in any geographic information system, on apps or different platforms, which restricts very much the access to the information. We also have very technical language to describe the phenomenon. Also, there is no visual distinction about the severity of the phenomena. This leads to everyone interpreting the severity as they can, and we also have no recommendations on what to do. So here is another example of how we work with users in consultation of warning thresholds. Beth mentioned something before about this work. So when the Met Service decided to change this warning system, as you can imagine, a lot of work and many questions arise on multiple levels. One of these questions was, how do we make sure that the thresholds of the new system are not only climate thresholds without having too much information about the impact? What else can we do? So we are one of those countries that are in the middle of the way, because we can improve our warning system, but the country does not produce systematized information of impacts in such a way that we can implement, for example, IVF. So what do? We decided to work on involving users in a part of this very complex conversation. We did a survey. But this survey that we did, it was at each weather service observation spot in the territory. But this survey had a special feature. It had to be completed jointly and by consensus by the leader of the office of the weather station and the local civil protection. This survey had to answer very specific questions, such as, for example, the one that you can see here. For example, from how many kilometers per hour the winds start to be a problem from the normal development of daily activities. So this question was repeated by several phenomena in such a way that we tie the experience of who makes the observation to the experience of whoever responds to a severe event at a local level. So this gave us an approximation and was a source of reference that came in comparison with the strictly climate thresholds. So to that experience, we add a database that you can see here in these maps, created by us with reports on social media and local media news in a determined period of time. And we also made some data collection through surveys that systematized the experience in terms of thresholds of operational forecasters, because many of them have 10, 20 or 30 years of experience in issuing warnings, and it was really necessary to be able to contrast this knowledge with the climate thresholds as well. So based on this information that you can see here, some thresholds were adjusted for 5 phenomena. These phenomena are wind, sonda wind, that is a special wind that have place in the Andes region of Argentina, rain, storm, and snow. So you can see it in the maps here in the bottom on the right side. So these thresholds, when the new early warning system is implemented, they will be published in our website. Okay, so two more examples about how we work with users, and this point in conceptualizing the warning levels. The system to be implemented had a preset definition by colors: green, yellow, orange, and red. So based on the comparison analysis and a review of papers that we did on risk communication and risk perception, we decided to establish 4 definitions for each color of warning and test them with a group of people with different profiles. For example, citizens without any knowledge of meteorology, meteorologists of our agency, and decision makers from the DRR arena. From these results, we can see not only what they understand, but also what they expect from an early warning system. So there is a final report done about this study. It is in Spanish, but I'm more than happy to share it with you. We use those definitions, these definitions actually, that user choose as the most understandable and those that prompt them to make a decision. So it is not just about interacting with users to see the thresholds, but also to make an understandable definition of each level and color of warnings. So as you can see, we also take advantage of this study to ask many other questions that help us to analyze different topics. Okay, so this is one of the last slides you will see full of information. This is another work that we did with users, but in this case, not necessarily with emergency agencies. So to analyze the colors and icons of this new early warning system, we entered a process of a study of understanding the iconography, and we made tests within our organization with people, again, with different backgrounds. And you can see how the icons were mutated here, for example, and here, this is Sonda Wind. And then we decided to use familiar symbols and languages, such, for example, road signs, to distinguish warnings with triangle shape. This is, and the advisory system that the early warning system includes itself as with rhombus shapes. But then we went further and work with another expert user in accessibility, such as the National Agency of Disability of Argentina. So they advised us on the web visualization and its levels of accessibility. And on the right side here, let me see, okay, here, you can see one of the exercises made for people with reduced vision that made us change, for example, the color palette of the warning levels. You can see the difference of the colors here. So this work is, in my opinion, outstanding because it is necessary to make the exercise of thinking about early warning systems and accessibility so that the system manages to cover the whole population. Okay, I promise that from now on the presentation will not have so much visual information. So now we already designed the system. We are in these previous stages before the implementation, and while our colleagues, meteorologists and developers are working hard on the implementation and testing, those of us who work with users decided to implement a series of workshops prior to the implementation, since it is extremely important that this system is not even an overnight news, especially for the DRR users. So during 2020, we established a work plan in which we reached more than 1,000 decision makers through a series of workshops and virtual trainings. Why virtual trainings? Well, of course, we were planning to travel around the country to train emergency agencies on site, but that was not possible because of the pandemic. So we put together a handbook for different decision makers that contains a detailed description of the system and includes all the thresholds, all the recommendations to the population, and details of how each area will be named jointly with its local government's nomenclature. So this work was done in the last 3 months. As you can see, we reached a variety of very important users who already know the system. Will be, although we will present it into the public in 20-25 days. So doing all this presentation process, not only in the work with emergency managers or different users, but also all the work behind the scenes of the med service team that was done from home in a pandemic context, I think this is the biggest effort to be highlighted at this point. Okay, so after the implementation, the system will be implemented really soon, as I said before. What are our plans to continue working on the new system with users? Well, I think of it as a cycle. Now we have to accompany the implementation using every channel available, but then start to work all over again to survey the uses, the weaknesses, the adjustment that will have to be made in the future, as well as to establish continuous collection, data collection strategy that will allow us to adjust again the thresholds annually with users, of course. Okay, here you can see a little bit about the system. As you can see, it is a system that provides warnings for rain, storm, snow, wind, and sonda wind, as I said before. It also provides information, but in a form of advisory for extreme and low temperatures, reduced visibility due to the presence of dust, smoke, volcanic ash, and fog. And as you can see, the advisory system has only 2 colors, and the color violet will only indicate that there is an active advice for those phenomena that I mentioned before. This has to do with the fact that we are still missing enough observations to be able to establish threshold levels as we are able to do with the other warning phenomena. But this is definitely something that we will work on in the future. So the whole system has an anticipation of 3 days and will be in CAP format. And this information will also be complemented by the short-term storm forecast, which is radar-based information, and the heat and cold wave warning system that is already in place. And we also designed a special service for emergency agencies that you can see here, this one, in which detailed information is sent to them every time there is an update of the warning on the day, so they can reply the information easily. Okay, so I'm very close to the end of my presentation, and I want to take advantage of this opportunity to highlight some lessons learned along the way regarding the evaluation of services from the perspective of different users. The first one, once you start working with users to update a service, it is not an end user anymore. The user is everywhere in your creative process. This is a very powerful concept of co-design. The second one, sustaining links over a long period of time increase the confidence in the participation of co-creation processes. So it is very important recommendation that there should be professionals specifically dedicated to carrying and maintaining these links. The third one, and I don't know why, but my favorite one, work with social sciences. Because, for example, anthropologists, geographers, sociologists specialized in disaster risk reduction, as well as communicators and the regular disciplines of any meteorological service have participated in the whole process. But this leads me to say that beyond the fact that the system has to be built on a profoundly transdisciplinary basis, it is an achievement that, for example, in each meeting full of colleagues from different disciplines, the question of most of the meetings was, what does the user want? What does the user need? Let's just find that out. So, and this is a great achievement in any meteorological service. The fourth one, share your question with the other DRR agencies that monitors other hazards, because they might have the same questions that you have. So you have to work together, because if you're able to answer those questions, it is possible that you may be improving the whole system, the whole DRR system. And finally, don't go back, because once you start working with users, you may want to apply these techniques in every weather or climate service improvement. and they will be really, they will be better services. And of course, you have to be patient, because as you can see, the work that I showed is a 5-year work. So you have to be patient, because progress takes a long time. So to finish, I want to share with you a testimony of a civil protection user who said these words in one of the last workshops that we made. He pointed out that he remembered when we went in 2016 to his town to collect his needs and the information on the use of the warning system. So the fact that he remembered these instances of contact, and that he understands that this information was used to improve the system, and therefore his decision making, was a small sample of how the risk management system with all its components fits itself and improves itself only if these relationships are built and something is done with it. So I hope this information was useful for you. That is all from me. Thank you very much.
Thank you, Hule. That was great.
We have one question from Marta Vinuka. She says, "Will the manual that you are showing, will this be available on the web?"
Yeah, well, we actually, this is a good question, because we made different manuals, handbooks for different users. So we have one handbook for the audience, the general public, and we also have manuals for emergency agencies. So if you speak Spanish, I'm more than happy to send the manual for emergency agencies for you.
Great. We have a slightly light-hearted one here, I think, from Harold Richter. Julia, how did you overcome user survey fatigue given the multitude of surveys you ran? It says, did you offer chocolate?
No, we didn't. I wish I could, but okay. Yes, that's a nice question. The thing that maybe it wasn't very clear in the presentation, that this was the work that we have done in the last 5 years. So it's not that we were, all the time knocking at users' door to please complete this survey, please complete this survey. It was not like that. And it is something important to be aware of, that it's not that you always are going to knock on the same user doors. Okay, sometimes you work with national organizations. Other times you need to work at a provincial level. Other times you need to work with the scientific sectors. Other time you need to work with local governments. So there is not this is not always the same user that we bother.
Great. Here's one from Darren Griffiths. Great to acknowledge the achievement in the context of the pandemic. Question, do you have a fixed lead time for moving from alerts to warnings? I'm thinking some phenomena can be warned with a longer lead time than others. Will your map show, and this is sort of a separate question, I guess, will your map show both alerts and warnings concurrently?
Well, yes, definitely. Actually, in the website, okay, I cannot go back to the presentation, but I didn't show in the presentation how the system will look like in the website. But in the website, actually, everything will be overlap. You can overlap warnings and alerts and different lead time information.
Okay, we have a few more questions, but we're basically up to time. I don't know, can I go through them, Beth, or?
Mark, we're doing all right. We can go for another 10 minutes.
Oh, okay.
So we've got 2 hours altogether. So we're
all
fine.
right. Okay, so you don't want to necessarily stick to exact program. Okay, so so Rob Taggart, haven't read this one yet. So traditional text-based warning products are still useful, as was demonstrated in the New South Wales bushfires, when some communities were cut off from the outside communication apart from radio presenters reading out text messages. Has your team worked on ways to overcome difficulties in user interpretation of text-based warnings?
Well, I'm sorry. I will read the question. Has your team worked on ways to overcome? Yes. Well, okay. So the one of those things that we identify in the text warnings, in regarding the interpretation topic, was the technical language. All right. Some of the text warning were the language was very technical. Not in all of them, but in some of them, and this confused the user, especially the emergency managers users, because the reality of emergency managers in Argentina is very heterogeneous. So they don't have all the same capabilities to understand what the information that they are receiving. So at this point, I totally agree that text warning. Actually, yeah, maybe I made a mistake in the presentation, because it seemed that our new early warning system won't have text at all. Actually, it will have text. Every warning has text related to it, so it will. But in my opinion, some of these flaws that we identify has been corrected in the way that we organize or reorganize this warning text, because it it is better organized. Actually, Rob, if you can write me an email that I can put my email on the chat, I can show you some of the work that we have done regarding your question.
Okay. Next one, John Nen. I don't really understand this question, but it's probably due to my poor English. But anyway, I like the social approach. Do you have epidemiological input into the development of impacts as well?
No, we don't. What I can say about early warning and health sector is that, for example, our heat wave early warning system was developed with the health ministry, and it has mortality impact information. But at this point, epidemiological input it's not on this early warning system. For now, I mean, I'm not. Yeah, maybe in the future, I'm sure we will have to, introduce that kind of information.
Okay, thanks. Marta says she speaks Spanish, so that's good.
Okay.
That's fine.
Gracias.
Steve Goodman, the use of dashboards seems to be gaining popularity. Can the user, say, emergency manager, drill down by clicking an icon to view radar or satellite loops in addition to numerical weather prediction fields?
Okay, drill down.
Sort of clicking in and seeing more information as you...
Yeah, definitely. Actually, all this information is complemented by radar images and satellite images. And actually, I have to say that I definitely agree with Steve, because emergency agencies tend more and more to use radar and satellite information to make decisions. But I also have to say that it's really important that Weather Service accompany this use of the satellite and radar information. Actually, we're doing that in Argentina in a local project that we have. Yeah.
Okay, so a comment from Harold Brooks. In our experience in the weather community in Norman, one of the valuable aspects of developing products with users is that you get a group of users who have an investment in the new product. They also understand the challenges of development and forecasting.
Yes, this is a great comment, because every time that we go back to the user or we try to explain, for example, it's a daily basis of knowledge for us, but when you go to emergency agency, even more if it is a local emergency manager, and you explain to them how complex it is to create a forecast and how many research do you have and how much information do you need, they start to understand why sometimes it's kind of difficult to not only to understand a warning message, but also to be accurate, to have accurate messages. Yeah, definitely.
Okay, Joanne Robbins, great presentation. Thanks, Julia. You mentioned the importance of building long-lasting user relationships. You do. How do you recommend maintaining these effectively? I'm thinking that with turnover in the responder community and the resource requirements to maintain these relationships, it might be quite challenging.
Yes, but you know what? I do. But you know what? I learned something from this pandemic context, working with user in a pandemic context. And believe me, it was not easy at all to work with emergency agencies during a pandemic and trying to train them on an early warning system, because, you know, we were not the problem for them this year. So it was really hard. But at the same time, we also depend a lot on traveling to the provinces, going to local governments, you know, and that is when you need, for example, of course, financial resources. But now with the pandemic, look how we reach 1,000 emergency managers from home. So I think that in the future, we will need to use more and more the technology to work with emergency agencies, and we will need to develop more and more different tools to develop this, to increase and maintain this relationship, but also to collect data, because we can be there, we can be together in the same place, at least for the next year. So in order to finish answering this question, we already have a plan for the 2021, and we already know how we will collect again and to reach again these users in order to understand how they are using this early warning system. And every time you get a call, you send an email, you ask how they are, or maybe post-event you call, and this is the way that you can keep a good relationship. So when you need some information, they will definitely come back to you and give you what you need. So it's very important. For me, as a sociologist, I can say that it's very important to be there for them and to build a relationship. This is something that usually is not mentioned in this kind of presentations.
Thanks very much. That's it from all the questions here. Thanks a lot.
Okay.
Thank you, Yuli. That was fantastic, and I think it provoked a lot of really interesting discussion too. So let's go on to our fourth speaker, Amanda, presenting on fire atmosphere model verification. So over to you, Amanda.
Great, thank you. All right, so I'm going to discuss the verification process for our Colorado fire prediction system, which consisted of a coupled fire atmosphere model. We developed this system in conjunction with the Colorado Center of Excellence for Advanced Technology Aerial Firefighting. Just wanted to show everyone real quick where Colorado is located. It's basically in the interior western part of the United States, in the circle there. We have mostly complex mountainous terrain, but there's also some plains to the east as well. And we wanted to develop a whole decision support system around the coupled atmosphere wildland fire environment, or COFFEE model, that would allow our fire responders to be able to run some simulations themselves on fires they're responding to get an idea of where the fire may be moving in the coming hours during their response. It's a whole decision support system, so we have all this input data and all these sort of display systems that the end user will use. But the real focus of our verification was this model. Specifically, the COFFEE model was adapted to the Weather Research and Forecasting, or WRF model, and is a module called WRF Fire. So I keep mentioning that this was a coupled model. specifically what that means is a lot of our fire spread models are driven by the atmosphere, the wind conditions, temperature, etc., that'll affect the rate of spread and direction of the fire along with the fuels and fuel moisture. However, the co-FPS also takes into account how the fire in turn will affect the weather. So instead of parameterizing how the fire's release of heat and water vapor into the atmosphere would then in turn affect wind direction and speed, updrafts, and that sort of thing in the atmosphere, the model actually is coupled so that the fire will directly impact the atmosphere. So I have an example here of a simulation from the WRF fire or co-FPS model. This was the last chance fire in 2012 in eastern Colorado on the plains that destroyed the town of Last Chance. On the left is the burned area perimeter versus WRF fire, which is in the blue, and then on the right is just an animation of the smoke concentration released from the fire. In this animation, we see at the beginning how the smoke is rising high in the atmosphere as the fire spreads. And then as we move into the nighttime hours and the boundary layer stabilizes, the smoke sort of lays down and isn't rising as high into the atmosphere anymore. So we can look at the weather portion of the model in the traditional way that we'll be doing verification. However, the wildfire spread portion was a bit of a challenge. When we look at weather, it's modeled worldwide. We're usually on a regular grid, but for our wildfire, we only have case studies. We can't do long 2 to 3 month retrospectives to see how our model is doing because we only have cases if cases happen, and then co-FPS is only looking at a 13 by 13 kilometer box around the fire. Weather's occurring constantly, whereas the wildfire, it'll happen, and sometimes we can get an idea if there are weather conditions that would support the occurrence of a fire or a really dangerous fire conditions. But until something actually sparks, until that person throws a cigarette out the window or lightning strikes, we don't know that a fire is going to occur. So we don't really have that forewarning, and we don't have, as I mentioned, that continuous set of data to do verification against. Also, when we look at weather, it's observed regularly every 3 hours, every 1 hour at set stations and to specific standards set out by WMO or other organizations. But when we look at the observations of the wildfire, that data is really collected to aid in the real-time response of the first responders, of the firefighters, and of the teams managing that fire. So they're taking observations as they need it to help their crew who are in the airplanes or on the ground. And it's not really with verification of a model in mind or putting observations into a model as we do with weather. This also adds an issue of accessing that data. We have our weather data in regular repositories. Different countries have different repositories, or maybe there's some wider regional repositories that the data is deposited into regularly. It's been quality checked, there's quality check flags on it, and it's in a format that we're comfortable using. But with wildfire, because this is just tactical data for responding to the fire, the data may or may not be saved at all. They might be archived somewhere that is not accessible to a researcher. It can be in any sort of format. I know one issue we had early on in the project was our data said it was in UTC time, but it was actually in local time. And so all our verification of our fires were off by 6 hours. So we had to go back and fix that and cross-check that. So those sorts of errors slip through easily. And then I've even been recommended to go into filing cabinets where some paper reports were saved with data I needed. So it's not as straightforward as it is with weather. So we really had to sit down and say, okay, what data do we have? that is in its best quality, that we can kind of see how well the system's performing. And one of the main observation sets we had were fire perimeters. On the left is an image from our multi-mission aircraft where they would fly the airplane over the fire, and either somebody would manually draw a fire perimeter based on this data, or one of our colleagues, Amy DeCastro, did work to automatically determine fire perimeters from these videos taken from the aircraft. An example of the fire perimeter on the right, showing the active and the contained boundaries in red and black, respectively. So these were, for looking at the fire spread portion of the model, these were really the most robust data we had. We still might only have them once every 24 hours, once every 48 hours. It's really chaotic, especially in the early response to the fire, just trying to get a handle on what's going on, where people need to be, you know, where is the most dangerous area of this fire that we need to stamp out. So these certainly aren't hourly perimeters or anything like that, but this was really the best data we had. And if you kind of look at what these fire perimeters look like, they almost kind of look like blobs of precipitation. So we approached it as if we were evaluating precipitation accumulations in the model. And one of the main metrics we used were contingency statistics. And here's an example for the 2018 season, the cases we had in Colorado. This is a performance diagram. We have success ratio on the x-axis, which is 1 minus the false alarm rate, and the probability of detection on the y-axis. And the great thing about these diagrams is that take advantage of the relationship between different contingency statistics, so that the curved solid lines are the critical success index and the dashed lines are the bias. And in the end, you really want your forecast up in the upper right. That's going to be your best or closest to perfect forecast. You'll notice that a lot of our 2018 case studies are in the upper left here, which means that the perimeter, the forecast fire spread overlapped well the observed fire spread, but there was also a lot of overprediction, high bias, high false alarm rate. And so that gets us to working with our end users and really taking the time to find out what's important to them. And I'll start with the bottom bullet here. The example, this overprediction we saw in the performance diagram wasn't really of concern to our stakeholders and the personnel working with this product. They were much more interested in what the direction of the fire spread was and if we caught that correctly. One of the issues we ran into in terms of overprediction as well is that it was difficult to take into account any mitigation strategies that our responders were using. So some of the overprediction was a product of the model not performing well, but some of the overprediction was also a product of the mitigation techniques and slowing down the fire or securing a part of that fire line that we didn't take into account in the model. The model is kind of a worst case scenario where if there's absolutely no response to the fire, how might it spread? But to get this feedback from our users, we had regular stakeholder meetings where we could present through the lifetime of the project, where we could present the progress we were making, some of the scientific advances, as well as the verification metrics and evaluations we did. And we could get feedback from them about how they thought the model was looking, if we were focusing on what they thought we should be focusing on, and get some feedback from them. In addition to just kind of the scientific process of developing the system, the stakeholder feedback was critical in getting observations. So I mentioned that we had a lot of difficulty verifying the model with the fire spread just because it's so hard to get those observations or not knowing where to go. So we could get the kind of feedback of, oh, well, that data you need to verify that is in a filing cabinet, you know, at this post. Let me help you get that paper report. Or you could talk to somebody who was a commander on that fire and they could say, oh, you know, I saw a pyrocumulus cloud go up at this time, or this was the time when the fire became really unstable. And so from a case study approach, which we had to take because of the nature of the wildfires, we were really able to get excellent observational information from our users. So in addition to informing the process, they also really helped inform where we can find observations for these forecasts. So I did mention that they were more interested not in the size of the fire so much as the direction and speed of the spread. And so in addition to the contingency statistics, one thing we were looking at was trying to adapt verification tools used for meteorological phenomena like precipitation for fire spread. And so one of the tools we looked at was the method for object-based diagnostics and evaluation time domain, or MODE-TD. And a schematic of how the tool works is on the right here, where your X and Y axes would be your spatial latitude, longitude, but your vertical axis is time. And so you can look at the evolution of something like a precipitation system over the course of a model run. And this tool is available as part of the model evaluation tools package at the link on this slide here. Because we saw some similarities between how fire spreads and precipitation spreads, we wanted to look at this. However, an issue we ran into is that this tool required hourly observations. And as I mentioned, we have a lot of trouble getting even one fire perimeter for a model run, let alone one every hour. So one thing that we have started exploring is doing some interpolation between the perimeters we do have, just to get a general sense of how the fire is moving through time. So the example here on the left is the 416 fire from 2018. This was one where we had a higher number of perimeters, which was 4 across 30 hours. And so we took the interpolation of this to get this finer scale assessment, just to try to get a sense of, you know, we could visually look and say, yeah, it looks like the model is capturing the direction and speed of the spread, but we really wanted to get that quantitative estimate. And I really wish I had some sort of numbers to show you, but this work was early in the progress when the project ended. So unfortunately, I don't have any numbers, but this was the sort of approach we were looking at taking to quantify that direction and speed spread. So the project is technically over. It was a 5-year project with the state, and the system is deployed operationally. Here's an example of that deployment. This is the interface that the responders and managers were used to working with. And so we adapted the outputs of our model in the running of our model to their display that they were already using. And this is an example of a fire that one of the personnel simulated from this year. He added an ignition point, and then this yellow boundary is the fire spread predicted by the model. And the red boundary is the actual perimeter of the model for that valid time. So here are some resources if you're interested in learning more about the project, or you're definitely always welcome to email me and I can take some questions as well.
Thank you, Amanda. So we have a question from Brian Golding. The WMO is thinking about whether exchange of hazard and impact data could be promoted with associated standards. Do you think this is possible?
I do think it's possible, and I think it would be extremely useful. How difficult or how long it would take, I'm not sure. It seems very hard to, if you're sitting in the room with folks, everyone's eager to get on the same page, but in terms of what standard you develop, how you implement it, and who's going to follow it, that seems like a bigger challenge. So I think it's possible, but I'm not sure how much work it would take.
Okay, a question from Beth herself here. How is spotting handled in the Colorado fire prediction system? So I guess that's where embers kind of start new fires. guessing. And in the verification, is spotting treated by any differently from the main fire spread region?
That is an excellent question, because that is one of the last things we tackled before the project came to its close. So you're correct, spotting is where embers from the main fire are lifted through the atmosphere, land outside the main fire area, and can start additional fires. And we have a module that was developed as part of CoFPS to handle that. And I'm not sure if it's implemented in the operational or not, though, because it was kind of at the very tail end of the project and it's still being worked on. But it's a parameterization where, based on the fuel and the fire behavior and the wind, a certain number of firebrands are lifted and dispersed in the model using, I'm not a modeler, so I might be butchering this, but there's some sort of a trace. You can do a particle trace in the model. And then the end result of that is a likelihood map. And so verification of that is going to be difficult and hasn't been done yet. First of all, just trying to find cases where spotting occurred and you can prove it occurred. And trying to verify a likelihood is a whole different method than trying to do something deterministic or even a probability. So we'll have to do more work trying to verify that. One thing we are looking at, one of our team members was in a fire evacuation area earlier this year, and she had a lot of firebrands falling on her as she was evacuating. So she was coming back and she was kind of taking pictures and collecting and seeing that. So we might be able to use that case because we had someone on the ground actually collecting firebrands. But it's kind of an open-ended question because it will be difficult for sure to verify that.
Okay, a question from Anonymous. What was the frequency of the stakeholder meetings? What was the duration? Who participated?
So I believe we had 2 to 3 stakeholder meetings a year. So it'd be about every 4 to 6 months we had stakeholder meetings through the 5-year project. They were usually an entire afternoon, so kind of 1 p.m. to 5 p.m., so 4 or 5 hours with a break in the middle. And the participants were our project managers from the Center of Excellence, who were consistently involved in managing the project. Other folks from the Colorado state level fire community that were interested, regional fire responders often came. And then we also had folks from Colorado's air quality prediction, who are meteorologists that were looking at smoke's impact on air quality and predicting that. So I don't think we had any local emergency managers. Barb, please jump in if I'm misrepresenting anything. Barb was on this project as well. But I think that's kind of firefighting community, regional and state level, and then our air quality folks.
There were a few people from the Weather Service, like some of the incident managers as well. I don't remember if you said them.
I didn't, thank you.
Yeah.
The question goes on to say, how did the stakeholder feedback information advance your project?
So I did mention a little in my talk how it helped with the verification part, but in terms of advancing the project as a whole or the scientific development of the project, I believe the stakeholder feedback was pretty integral in what areas of the science we focused on. For example, Beth brought up the spotting module, which I neglected in my presentation, but the development of that module was because of the interest of our stakeholders. They were concerned about spot fires and predicting spot fires. So just that the whole development of the module was influenced by the stakeholder feedback. They also helped us know if we were doing a good job or not, if they were happy with the forecast or if there was something lacking in the forecast that we needed to address.
Okay, there's a question by Brian Gordon, but I think it relates to Julia's talk largely. So maybe we'll come back to that at the end, if there's going to be time for a general discussion at the end. So does this one from Jonathan Vai, I think I got the name right. Does the Colorado Fire Protection System provide any information on the severity of the fire at a given point, e.g. ground fire, single tree torching, intense crown fire? If so, have you been able to do verification based on after fire assessments of vegetation damage?
So I believe, and Barb, again, feel free to jump in. I believe the main output that has to do with severity of fire would be flame length. And that's another example of a parameter that stakeholder feedback is the reason we included it in our output. We have not been able to go out on a fire and do a post-fire analysis and do any sort of vegetation-based assessment. But we were looking at video from the aircraft and seeing if we could get an idea of the flame length, because sometimes they would zoom in on a single tree, so you had a video of a single tree on fire, and if we could get an idea of how tall those trees were, maybe we could get an idea of that flame length. That didn't go very far. Another thing we did to address intensity is we used the video to try to do some case studies on pyrocumulus, because our stakeholders told us when they see a pyrocumulus cloud form, that gives them an indication that the fire is or will shortly be very unstable. And so that's something that they were concerned about. So we haven't done anything directly addressed in your question, but those are two phenomena we did look at.
And a question from David Hoffman, which I guess could also relate to that previous question, but he's asking, is video footage and photographs from social media used as additional information to estimate the perimeter? So I guess it could also be for intensity and things like this. I assume that information is often posted in real time.
So we haven't used social media for the perimeter. It can be a little difficult because you would need to have some sort of GPS location associated with that video. And sometimes social media does have that and sometimes not. It would be a bit labor intensive for the resources we had. But what we have used social media for was identifying cases. We were looking at impacts like air quality impacts, which people would post on Twitter or Facebook or other social media. And then also looking at evacuations that happened and how it impacted the public, and that helped us choose cases we focused on. We also use social media for identifying pyrocumulus cases.
Okay, thank you. That's all the questions we have here at the moment.
All right. Thank you very much, Amanda. That was really interesting. And as someone living in Australia, pretty relevant to us here as well. So at this stage, we've got just a couple more minutes, about 5 minutes until the end of the session. And so I'd like to invite people, if they've got some more general questions that they'd like to raise, to post anything through the chat, and we'll keep an eye on that and see if there's any more discussion that people would like to have.
So I did mention the one from Brian Goulding. He was saying that your question raises a key issue between warning systems in different countries. So the US Advisory Watch warning system is one way of working. At the other end of the spectrum, the UK warning levels are distinguished by risk, but all are called warnings regardless of lead time. So I guess that sort of relates to this sort of coherent treatment of standards, I guess, associated with it.
Julie, would you be interested in saying a few words about that one? I don't know to what extent the Argentine system was consistent across the country and takes one approach or the other. Any comment?
Yeah, well, I know that, well, hold on a second, please. I know that, well, with the experience of the last year working in the WMO environment, that it is really concerned to each country, what they call a warning, what they call an alert, what they call a very short-term forecast. In Argentina, all this, what in some places is called a warning, we call it a short-term forecast. For us, we call a warning, at least in Spanish, which I would say the word is alertas, which is very similar to alert, but we call it a warning. It's the 3-day usual warning. So I think this changed from country to country, right?
Yeah.
Could it be if these warnings are put on social media, then they may start to have some kind of coherence across countries and things? If they're sort of put on Facebook and things like that, people have to know what it kind of means.
Yeah, definitely a weather service should work with a communicational framework in order to explain the public what is a weather warning, what is an alert, what is another kind of weather service. Yes, definitely there should be a communicational framework to accompany this kind of services, because if otherwise people don't understand what's the product and what's the difference between one service and another. Yeah, definitely.
So Meteoalarm and the European EMA and projects through UMetNet and so on must have had to deal with this with all of the European countries. I wonder if there's some things we can learn from their experience. If anybody's got any comments, it would be great to, if you're able to speak, there's only a small number who can do that, but or post something in the chat. It would be interesting to know. Okay, we have a comment from Bob Goldhammer that nomenclature is sometimes the biggest problem. That'll be true. All right, well, it seems like we've come to a pretty good stopping point for today's webinar. I'd like to thank all of the speakers today and also thank Martin for his wonderful support. And I'd like to encourage all of you for, thank all of you for coming today and posting some really good comments and discussion. We'll try and make this available. Certainly the presentations will be made available afterwards and recordings. And you should get an email from Martin in the course of time on how to access these. Don't forget, next week, the webinar is on hazard modeling to be led by the modeling task team. So please do come along if you can. It's similar sort of time as this one. And with that, I'll say thanks again and goodbye. Enjoy the rest of your day, night, morning, whatever it might be. Thank you.